this rendition of the KITP NSBP Innovate seminar. Today we will have the honor of hearing the talk called Rousing the Quantum Vacuum, Ephemeral-Pair Dynamics on Sub-attosecond Timescales. And let me introduce our speaker for today. Our speaker is Wendell T. Hill III, a professor at the University of Maryland, College Park. He has appointments with the Institute for Physical Science and Technology in the Department of Physics, is a fellow of the Joint Quantum Institute, JQI, and the director of the Interdisciplinary Graduate Chemical Physics Program. As a native Californian, he was born in Berkeley, grew up in SoCal, and educated at the University of California, Irvine, with a physics BA in 1974, and Stanford University with a physics PhD in 1980. He left the Golden State, much at the behest of his bride, who earned her graduate degree at Columbia University, for a 2-year NRC postdoc at the National Institute for Standards and Technology, or NIST, after which he was recruited and joined the faculty at UMD. Hill has held visiting positions at institutions in Asia, Europe, and South America, as well as in the US. His research interests and journal publications range from high-energy particle physics to the ultras in atomic, molecular, and optical physics, or AMO, ultra-intense, ultra-fast, and ultra-cold, with an emphasis on quantum dynamics. He has also authored an article in the Encyclopedia of Applied Spectroscopy, an AMO physics textbook, and an ebook on the quantum vacuum, which is his primary scientific pursuit today. Finally, he has served on several scientific advisory committees, domestic and international, was the program officer of the AMO program at the National Science Foundation, and has been honored with an election to the American Academy of Arts and Science. So without further ado, please take it away, Dr. Hill.
Okay, well, thank you for the invitation. Appreciate everybody showing up. So I'm going to talk a little bit about some of the things that we do, and if you have questions, I understand somebody will read them to me. If there's something that's not clear, please go ahead and ask the question. That's perfectly fine. We're interested in looking at effects that come about when you take an extremely intense laser and focus it down into the vacuum. So if we have an intense enough laser, turns out we can sort of stir up the vacuum, which is what I'm going to talk a little bit about today. So again, if there are questions as we go along, please stop me and we can try to address them. Okay, so light goes all the way back to the beginning, and I like this quote from the Bible of, let there be light, and there was light. And so that's where we are, and that's where we're going. I also like this quote from J.J. Thomson, which talks about how light has allowed us to study things and develop theories that can change. And we will see that the story of light itself is particularly like that. So we think we understand something, we do some experiments, often with light, we change our mind, and we go on. So this is apropos, and it's even true today. Light, for example, actually started before the 5th century here, but first it actually came out, they thought basically light was sort of this corpuscle type of idea, these two Greek people, and that was sort of codified with Newton, who actually used that word, and that lasted for about 100 years until we had Young came along, and then he had this did this experiment, the famous experiment, which showed that light was a wave. And so light was a wave in those days, and people almost completely forgot about the fact that Newton had this corpuscle idea. But then 100 years later, we end up with quantum mechanics, where classical mechanics was not giving us the right answers to experiments. And this whole idea of wave-particle duality came into existence. So light, depending upon how you are looking at it, what it's doing, It can behave like a particle. It can behave like a wave. And so that is where we are now. And we'll see even now, and what I'm going to talk about is that most of the time when we have a laser, we're really looking at the classical nature of it. We can look at it as a wave, but then there are also particle features that will become important. So light for a long time was basically incandescent, okay, incoherent, and fire's been around for a long time, and so the lights were rather weak, and you couldn't do a lot of nonlinear type of things. You could only do linear features until the laser came along about 40, 50 years after quantum mechanics came into being. And now we have a new source which is coherent and allows us to do a lot of things. Now, of course, when the laser was first developed, it was rather weak. But today we have much more powerful lasers. And this plot here is sometimes referred to as the Moore's law of intensity or power, where we see that we started off here with relatively weak light. Get my pointer up here. So we had pretty weak light down here at the very beginning of the lasers, okay? And then it quickly became more intense when we understood that you can store up light in a cavity and you can all dump it at one time. This is what this Q switching is all about. And that was pretty good, but then it sort of stalled out for a number of years here, and nothing really happened. The intensity didn't go up very high. But then we had the breakthrough of this, what's the CPA, which is a chirp pulse amplification, where one understood that, well, in order to, let's see if I can get this, in order to amplify this light, if you want to not destroy your optics, you need to make sure that the peak power is manageable. So you basically just stretch the pulse quite a bit, and then you amplify it. But you have to stretch it the right way so that you can put it back together, and then you can get high intensity. You can see this, it's just sort of scaling up, and we're up around this area right now. And I have a few thresholds here, which I'm going to talk about. And eventually we want to get up into this range, and up in this range, what's going to happen, what's predicted to happen, is the vacuum will decompose. Okay, so that's where we're hit. Now, light, when it's CW in particular, or when it's very low power, or if you have very low gain, it typically has a Gaussian distribution. So you go out from its peaks at the on axis, and then you go out, it falls off with the Gaussian shape. But what happens when you get really intense lasers is that we have high gain, and the gain then saturates across the entire beam. And so the highest power beams that we have today, oops, go back here. The highest power beams we have today, go back, sorry, my mouse again. We see that it's sort of flat all the way across. So if you take a line out across in any direction, we have a flat distribution. So the beam now, instead of being a Gaussian beam that's being propagated, you basically have a cylinder of light that's being propagated. And that has real consequences when you try to focus it. But that is what we're dealing with right now when we have really high intensity. So we've gone from a few milliwatts down here to a few milliwatts up here to about 10 petawatt. And there's a laser being designed right now, which I'll tell you a little bit about here in a second, that will even go higher than that. Okay, so now this chart tells us something about the light that we're looking at. So you can see that there are two axes, actually three. We have the pulse width down here, and we have the pulse energy here, and then we have the effective power over on this side. And then these diagonal lines tell us how the energy and the power and the pulse width all work together. Now, depending upon what experiment you want to do, what your goal is, you want either high energy or you want high power. So if you want to create fusion, for example, at NIF, so we need a lot of energy. So we have megajoules of energy that come through that beam. But the beam is fairly long, has a long pulse, so it's not very short. But if you want to rouse the vacuum, like where we're headed, then what you want is high intensity, actually. And so the intensity basically is the energy divided by time, and then divided by the area. So if you take a large energy, short amount of time, focus it tightly, you're going to get into this regime. And again, we have these thresholds, and we're going to talk about what happens scientifically when we have these various thresholds that we can see. Okay, so now let's try to do that. At the lowest threshold, and this is your garden variety lasers, you have your dye lasers, your Ti-sapphire lasers, your typical lasers that you will find in many, many labs, in physics labs, chemistry labs, even some engineering labs. What we have here at the beginning is that we do a lot of spectroscopy. So a lot of your laser spectroscopy is done at these relatively low powers. If you want to do, you want to have high fidelity in terms of the wavelength or the energy of the pulse, then you want to have a CW pulse, which is handled very well. So you can look at very, very narrow features. And this is what is shown here in this cartoon here, what we have doing just typical laser spectroscopy down here. So that's what the first range. Now, if we increase the intensity a bit, then what happens is if we put anything in the beam, it's going to ionize. And so that intensity range is about 10 to the 14 to 10 to the 16, particularly if you get to about 10 to the 16 or so, that no matter what you put in the beam, it's going to ionize. And so you will ionize everything. And so you can do a lot of things that way. You can do nonlinear optics. And this cartoon here shows high harmonic generation. You can generate X-rays, which can be very short in duration. You can do things like see photons being absorbed in the vacuum, something called above threshold ionization, for example. All of these things sort of happen in this regime. If you're not too intense, basically the laser is still a perturbation on the electric field of the atom or molecule. Now, if you go a little bit higher, then now what you see is you're in a regime that I call the relativistic regime. And so what we have now is that if you look at the this expression here, we basically are looking at this A here is the vector potential. And you can rewrite this vector potential and this momentum here in terms of a work, which is the electric field times the charge times some distance. That's basically work, because E times E is basically a force. So a force times a distance is a work. So we have a work here, and if we compare that to basically the energy of the electron, then when that ratio becomes 1, this puts us in the relativistic regime, which basically means that in a single cycle, the electron puts up enough energy to start to approach the speed of light. And this A naught has no limit per se. There is sort of a limit, but we're not anywhere close to that. And so the electron becomes relativistic. And so now we have lots of different things that we can do. This is known. We call this the classical parameter for intensity, basically. But we can start to study strong field effects. Again, now the electric field is the laser is no longer a simple small perturbation compared to the internal workings of the laser, internal workings of the atom or the molecule. So we have to take that into account. We also have relativistic effects. We can accelerate the electrons, and so you can start to think of developing accelerators that now start to compete with Linux, but only over a very short space. Now, the reason for that is that typically you've been told that when you put an electron in an electromagnetic field, you only have to worry about the electric field. And that's generally true because the electric field magnitude and the magnetic field magnitude differ by about the factor of c. However, when the velocity becomes close to c, these two electric and magnetic forces are comparable. And so what happens now is that if you use your right-hand rule, we have the force due to the electric field is along the electric field, and then V cross B gives you a force along the K vector. So now we have a way in which to accelerate our electrons along the direction of the laser. We can get energies of multiple MeV. So these become very, very relativistic. And that's what people are doing. In fact, they're using this technique, not necessarily vacuum acceleration, but there are other clever ways in which to do this to generate 10 GeV electrons. Finally, there's some dynamics of the electron and how it behaves in the field that one can exploit to actually learn about the intensity. Turns out it's very hard to measure the intensity of these fields, but using the dynamics of the electron in the field gives you a way to do that. The next regime here, I call it the vacuum regime here, where the vacuum now responds to the electric field of the, well, actually electromagnetic field, the light itself of the laser. Now, what do I mean by that? Well, first of all, this A naught can get very, very large. It could be it could be 1,000, multiple thousands. Now, if you imagine the electron is very light, and now you can put protons in here, and the protons now can behave in a similar way to the electrons. And so now protons can be accelerated to relativistic speeds. We're not quite at the regime where we have enough intensity to do that, but we're starting to approach that. So you can think of building an accelerator for protons and maybe even ions as you go higher and higher and higher. We can look at the strong field QED. Now, quantum electrodynamics is one of the most studied and theories we have, and it's very well documented. You did multiple digits in terms of making measurements, but all at the low intensity regime. Now, at the high intensity regime where we want to study, it hasn't been studied so well, and that's what our goal is. If you're going to study a vacuum, one of the things you have to do is have a vacuum. So it turns out it's not so easy to make a vacuum. You can plug in a vacuum pump, but you don't suck out all the air. And so you have to come up with clever ideas. And we have one that we have done, and I will give you the reference to that here a little bit later. We don't have time to go into all the details. But what we really want to do is that we want to stir what's known as the virtual particles in the vacuum, and I'll tell you a little bit more about that here in a second. But this is where we are going here. Now we get to this upper regime here, where, as I mentioned before, the vacuum actually can break down. That is to say, what's going to happen here is if we have a laser that comes in, this laser now will then spontaneously create matter. Electron-positron pairs. And that is because we have a field that's so intense, we have an expression that looks very similar to the A naught, except for now, instead of the work being done over the wavelength of the laser, it's going to be done over what's known as the Compton wavelength. And that turns out to be special because, and I'll tell you here in a second, that's a wavelength beyond which we can take two pairs of electron and positron, a pair of electron and positron, and separate it enough so they can become real. And let me explain how that works here. So now with this introduction here, this is what I'd like to talk about. And we obviously don't have time to go through all of it. but we will look here at the quantum vacuum. I'll just define exactly what I mean by the quantum vacuum. We'll talk a little bit about what we can learn. We will look at a few experiments that can be performed, and then there are going to be two regimes. They're going to be the regime where the parameter I just gave you, which is sometimes called the quantum critical parameter, is going to be larger than 1 or less than 1, and that's what we're going to talk about. And then we will not have time for me to talk about how the technical needs that we have to build in order to study these things. But again, I'll give you some references to things that we have already done. Okay, so what is the quantum vacuum? Well, let me start off with the classical vacuum. The classical vacuum, everybody knows. It's devoid of everything. There are no particles, there's no energy, there's no light, there's nothing. It's a classical vacuum. Quantum vacuum is very different because it's the lowest energy state. It's the best way to say it. It's the lowest energy state. There are no real particles. I emphasize real particles because there's something called virtual particles, which I'll tell you about here in a second. There's no real particles, but there is something called fluctuation. So even in the lowest state, there's quantum fluctuation that we have to deal with. Now, there are different types of vacuum. There is, and I'll give you 3 examples here. There's the quantum electrodynamics, which basically talks about it's classical electrodynamics, which has become quantized, okay? So classical electrodynamics is relativistically invariant, so quantum electrodynamics is as well, but now you're going to add the quantum features to it, and there are lots of interesting things to this. And we know that this quantum electrodynamics has answered lots of questions, and it was awarded a Nobel Prize here as we see. Now, so the quantum vacuum, and we nicknamed that the QVAC here, basically is composed of electrons and positrons and light. And so this is a gauge theory, and so we have the fermions, and then we have the bosons. Now we can go to QCD, quantum chromodynamics, and we have a similar thing, except for it's more complicated. You have bosons, which are multiple types of bosons, and we have quarks, which are the fermions, but it's the same idea, but more complicated. The masses are higher, and so it's going to come into play when you try to study that. There's the weak forces, which I'm not going to say anything more about, but you can come up with a vacuum for that as well. But we're going to focus on this QED, this QVAC, and that's where we are going to land because the lasers that we use and the intensities we can reach are just now at the threshold for where we can actually do some work. All right, so what is this quantum vacuum? So the Schrödinger equation came at the beginning of the last century, almost 100 years ago now, and it answered lots of questions that classical mechanics could not answer. But it has some issues. Okay, it had some issues. It couldn't tell us much about spontaneous emission. We had to artificially think about how to handle that. Didn't tell us anything about spin. We had to artificially put that in. So there was a need to have a relativistic version of Schrödinger equation, and this is what Dirac did. So he came up with a way to do this, and so he has an equation. The equation has solutions. It turns out it has 4 solutions. 2 of those solutions, very familiar with, gives us the energy states and it gives us the spin. So great. All right. So that's a success. But it had 2 more solutions, and those other solutions were negative energy states. Now, negative energy in and of itself is not a problem. That's how we look at orbits in a classical system. That's what we do in an atom. We have negative energies. Fine. But the problem is that just like the positive energy states, the negative energy states were infinite. And so there's a question of, well, if they're infinite and atoms want to be in the lowest energy state, then why don't they fall in? Well, he had a brilliant idea. He said, okay, well, let's fill them up. You fill them up with electrons, so therefore, because they're fermions, they can't fall in. That satisfied that. There's this energy gap between these 2 states, And now we have an issue here that it was quickly understood that now if I take light, why can't it excite it? Just like you do in a solid, just like you do in an atom, you can excite it from the lower energy states to the upper energy states. Great. So now we have an electron and positive energy states and the negative energy states. We have a hole. Well, how do you interpret that hole? Well, that hole here we interpret as a antiparticle. And this was the beginning of antimatter. And so now we have an electron and a positron. The hole now was the positron, which was predicted and obviously actually observed. All right, so we can fill the bottom, we put a hole, and now we can have electron and positron. So now we could have two things, and they come together. When you pull this electron up, you get the hole at the same time. Okay, so now we can say that we have electrons that can be real, and so you can capture them, you can come up with a detector, you can catch them. But now what do we do with those electrons in the negative energy state? Well, those are now going to be virtual, and by virtual, that means you can't catch them, they don't live indefinitely. But in a sense, they're artifacts, but we can then use them. They do affect what we actually see. So let's come back. See the vacuum, the real and the imaginary, or I guess I should say virtual. And so now we have this Dirac C, and we can have the electron that we can excite. But we also have another feature that happens here. We have something that we have some fluctuation. So first of all, I should point out that the real ones, as I mentioned, can be captured. They have to obey this energy conservation, momentum conservation, okay? And you can have the virtual ones don't have to, and they can be what's known as off the mass shell. But depending upon how far they are off, they have to obey this uncertainty principle, and they live different amounts of time. So there's another way I like to think about this too, and that is that the fluctuations, we could have these things spontaneously fluctuate. So that's a tenet for quantum mechanics, fluctuation. So these electron-positron pairs can fluctuate spontaneously. And that's what we're going to deal with here with our big laser. Now, there's a long history of what people have tried to do. Let me just sort of rifle through this thing. Let me get to the so-called Wright-Wheeler collisions. So now you can have photon-photon collisions, and this should give rise to electron-positron pair. So if you take the right energy electrons, photons, and put them together, they can collide. You can then get an electron pair. This has been a search for a long time. Here's the Feynman diagram that describes this, and this has never been observed. And it's never been observed because the cross section is enormously small. So if you're in the regime where you have high energy photons, that is, the photon energy is larger than the mass of the electron, then the cross section is roughly somewhere like 10⁻30 centimeters squared, and that's and it goes down from there. And we can see this diagram. It peaks here, and then it falls. Now, if you go on the other side, you can actually write down an expression, and we see in this case that the cross-section falls as omega to the 6th power. So that means that this thing gets enormously small, and we can look here at if we take a Ti-sapphire laser, 800 nanometers, it's 1.5 EV. We see the cross-section is really tiny, and so you don't see this very readily. So it's really hard to see. Of course, it gets better if you go to somewhere in the X-ray. So if you have an X-ray, you should be able to see this a little more readily. All right, so what can we do? All right, if we take multi-photons, this is it becomes a possibility that we can look at the fluctuation here, and we can actually capture this. So let me just quickly go over this. You have this electron-positron pair, which comes into existence briefly and goes away. You can ask the obvious questions: how far apart do they get? You can do that calculation. It's pretty straightforward, and you get a number that's on the order of the Compton wavelength. This is what I told you before. So this is how long they can be apart based on the uncertainty principle. You can also ask how long they take, how long they will last, and you can do that calculation as well, and you get something that on the order of a half a sub-attosecond. So they don't last very long, they don't go very far apart. Then you can ask the next question, okay, how much work do you have to do in order to capture this thing? Well, that too is a straightforward calculation. I've already sort of given you how to do that. You can take the force, and then you can that's the field, and you ask how far you want to move it apart. Well, you have to move it beyond that Compton wavelength, and if you do that, you can figure out how much energy you need to do that. And this is something called the Schwinger limit, and we have an intensities that are on the order of 10 to the 29 watts per square centimeter in order to do that. And we're nowhere close to that at the moment. The intensity record is about 10 to the 23 watts per square centimeter. So this chi value that I told you about, this is this ratio between the work required to move at that Compton wavelength divided by the mass of the electron, that is enormously small. And so we're not in that regime. So there's some laser facilities coming online, which are getting us closer, but not exactly there. The latest, I will give a plug in for this opal laser. This is now in the conceptual design phase, and we hope that it's going to get built. If you're interested in this, I would encourage you to go to this link here. I have to show the link. There's a link up here, and put your name on the list and say that you're interested in having this thing built, and so we can make these studies. Okay, that laser is going to get us really close. It's going to be two 25 petawatt lasers, so it'll be 5 times more intense than the one that I showed you at 10 to the 23. So that should get us much higher in intensity. Okay, what can we study? Well, there are 2 different components, and I'm starting to run out of time, so I can't go through all of this. So I'll just go through this quickly. We can be in the low chi regime, if you will. That is, we're going to be in intensities that are not high enough to create pairs, but there are lots of things we can do to tickle the vacuum, and I'll tell you what that is. We can be in the other regime, where you can get pair production, and we can't get it directly, but we have to go through this sort of black box here, and I'll tell you briefly what some of those things might be. So there are plasma type effects. There are let me just put these all out here. There are laser plasma effects. There are effects for particle beams. That is, we're going to collide the electrons off particle beams, photons off particle beams, and all of these are meant to try to get us up into the regime where we want to work. The only experiment that's ever been done that's gotten us close is the so-called E144 experiment at SLAC a couple decades ago, and there's attempts to redo that experiment. They have a good chance of getting there. So we hope that we might be able to get there at some stage. There are other features here where, again, we can use a plasma. We can interact the lasers with plasmas, and that should get us closer. There's some things that we can do right now by mixing sort of plasmas and intense fields. We can create electrons. Those electrons can be accelerated, and they can help with the intensity needed to stir up the vacuum, and we can cause what's known as a cascade. I'm not doing any of those kinds of things, so let me quickly tell you the kind of thing we want to do, and that is going, again, back to the beginning of a photon-photon scattering experiment. That is really looking at the photons scattering off of each other and those photons now can scatter elastically, inelastically, and we want to measure some of those features. So quickly, there are Lagrangians which tell us what's supposed to happen, and in those Lagrangians, we have the most important part is the fact that the Lagrangian tells us that depending upon whether we line up our laser and we propagate another beam perpendicular to that alignment or parallel to that alignment, we should see a birefringence of the vacuum. And that's there's been a lot of effort trying to see that birefringent. Again, it's very, very small, very, very hard to do, but we're getting closer to being able to do that. This box diagram, which is on the screen now, is the famous diagram that one would like to try to see. Okay, so these theories, there's lots of different theories, but I won't go through all of those because we don't have time. But I do want to say the following, that what we want to do is, I told you, I showed this cartoon, we have these pairs randomly coming into effect. If we send a strong enough laser beam, we can line them up, as you see here in the diagram. And when we line this up, it's going to look very much like what you would see in a dielectric, where you run a large magnetic field in a dielectric. You polarize the dielectric. We're going to polarize the vacuum, and that's what that's the goal of what we'd like to do. So how do you do that? Well, there are lots of different ways to do that. Let me just jump because it's don't have time to say all of these things. Okay. Here, the simplest possible thing to do is we take two very large lasers, we let one polarize our vacuum, and we let the other scatter. And it turns out that if you know the scattering properties of your beam, now we go back to the Gaussian beam. We know how a Gaussian beam behaves. We know how the scattering properties of the Gaussian beam, and we have the minimum scatter, and then we can look for scatter that's outside of that. Very hard experiment, but that will then allow us to determine the scattering cross sections for either parallel or perpendicular type of propagation. And we've done calculations here, and we know that at 10 to the 24 watts per square centimeter, we should see a signal. This is not the only way to do it, but this is one thing that we have shown. So you can read about that in this paper here. There's a reason for doing all this stuff, and that is because it'd be nice to verify that the nonlinear components of the Lagrangian are actually correct. But there's another reason to do that, and that has to do with dark matter. There are axion-like particles that you may have heard about. It turns out they have a Lagrangian which is similar in the photon sector, and they would produce a change in the scattering properties that we would see. And let me just show you this picture here. This picture here on the right shows you the dot here is what QED tells us we should see. And if we have axion-like particles, depending upon what they are and what their properties are, they could move this point either to the left or the right or up or down. And so if we do a precision measurement on the vacuum, which we want to do, then you would be able to determine whether or not there's something else besides just the QED producing the vacuum. There are lots of different ways to do this. One of the ways that it looks very popular here is at the European X-Feld is to use X-rays. Again, if you use X-rays, the cross-section goes up. The problem is always that you're looking for a very weak signal and a very large background. And so they have a clever idea of blocking the stray signals, and they can look in the dark. And so this looks like a very promising possibility. Another possibility here is to do a four-wave mixing. So the vacuum, I told you, the vacuum looks like a dielectric. So you have a dielectric or you have a gas. You can do four-wave mixing in the gas. You can do four-wave mixing in a crystal. You can do four-wave mixing in the vacuum. And so this is a planned experiment, particularly at that Opal facility that I mentioned. Again, a very, very hard experiment, but this has the advantage that you're going to be looking for a signal in the dark. So we have these big lasers coming in, the light blue and the purple, and then we're going to look for a signal along the red, so it's in the dark, and so it should be better. Okay, I think I have gone beyond my time, so let me summarize here. I'm happy to answer some questions. Here's some things to remember: that we have some thresholds and some parameters that are quite important, and you can understand these things. So this A naught become relativistic, either with electrons or protons, when if you take the work it takes to move the entity, the electron or the proton, the wavelength, when that energy becomes comparable to the mass of the particle, then you're in this relativistic regime, and the electron or proton or whatever you have becomes relativistic. That leads to acceleration, and things become different. Another parameter is that now if you do that same experiment, you have a field, but now you're looking at the work it takes to only go a Compton length. So now you're going a lot smaller, and you do the same amount of work. Compare that to the mass of the particle, in this case electrons, you then should be able to make pairs. That is, the vacuum breaks down. It would work with quarks as well, except for their mass is much larger, you need much higher intensity. So electrons are the lightest things we know. By the way, there are predictions of lighter particles that we've never seen, and so those too would come out if we do these types of experiments. We talked about the property of the vacuum, and we talked about virtual particles and what that means. We talked about quantum fluctuation. We also looked at some testing that we could do. I didn't have a chance to go into much detail there. We talked about cross sections. We talked about some various types of experiments that could be done. We didn't really talk about that, but we talked about the standard model. Now, there are properties of the vacuum that are really quite important, and there are technical needs which I didn't have a chance to talk about at all. But here's a summary of some things that we have done, some experiments that we have done. I told you that it's important to measure the intensity. We don't know how to do that. I told you that with the dynamics of the electron, we can exploit that to look at the intensity. We have 3 papers that we have talked about that here, that I've shown here. Looking at the focal volume, in order to get the best intensity, you want to make sure that your laser does not have a lot of aberrations. We have studied that, and we have been able to link the electron distribution, angular distribution, to the aberration, and so that's a way forward to minimize that aberration. And we've studied that a few times, and we have some ideas of how to use AI, machine learning, and things to work backwards to maximize the intensity. I mentioned that if you're going to study a vacuum, you need to have a vacuum. We've done one experiment where we showed that you can use the laser actually to create a better vacuum. So you do the best you can, you buy the best vacuum you can, and then you can use your laser to improve it, because mostly that's left are protons. Protons, because of electrons and protons, come from hydrogen, and so we can clear those things out, and we showed that that can be quite effective. There's a bunch of investigations that could be done. One of the things that we don't know much about, and that is at these high intensities, how does ionization work? Is it the same as it is at low intensities? It's not necessarily the same, because we now have these the relativistic electron distributions. So we are in the process of trying to learn how to do that, and we're setting up experiments to do that. And we got a lot of other ideas. So one thing I should say is that we're always looking for good students. So if you're interested in some of these processes, please get in touch with me. So this is not a work that I'm doing on my own. We work in collaboration with several people around the world. We have students, too, who do all of the work. They get a chance to actually play with the toys. I just have to try to generate the money to get the toys. And so here's a picture of a group of people that have been doing experiments. They graduate, so they're going to leave pretty soon, but you can come join us and be part of this team. Let me leave you here with one thing that I've written sort of an article which is sort of non-technical, but it talks about the same thing I just talked about and a little bit more. So just the URL. There's a video which introduces this, and then you can you download this ebook and take a look at more things here. So let me stop there. I know I'm over. Thank you for your patience, and I'm happy to entertain any questions you might have.
Thanks for that, Dr. Hill. I'll hand it over to Carlton to look at the Q&A.
So, Dr. Hill, thank you again for the great talk. The first question is from William Phillips. He asks, would you say some more about the difficulties of focusing a flat top beam compared to a Gaussian? How much is the intensity reduced compared to focusing a Gaussian beam of similar total power?
Okay.
And do you have ways to work around the problem?
Okay, yes. If you take a Gaussian beam, all right, let me back up. So focusing is basically taking a Fourier transform. So when you focus a beam, if you go back to the optics, it's the focusing optics is exactly a Fourier transform. So you're looking at a Fourier transform in the focal plane. And so if you have a Gaussian, the Fourier transform of a Gaussian is a Gaussian. So you get the Gaussian back. So you get a central peak that peaks at the center and then falls off the Gaussian on the outside. So that's pretty straightforward. If you take a disk and focus it, what you end up getting is an airy disk in focus. So you get a solid disk that comes in, put it through a lens, and then you get airy rings. So you get a central spot which looks Gaussian-ish at the beginning, but then you get rings, and so you have a lot of energy you're losing on the outside. You think at these high powers, we think we're doing well if we get 50% of the beam in that central part. You can do better, but you got to work really, really hard. You have to have no aberration. So you're losing about half the beam in the outer rings of the beam. So that's one problem. And so that is well known. You can do that. You know how to handle that. But there's another problem, is that if you want a really tight focus, now you have another issue that happens, which is not really well known. If you go back to Born and Wolf, they've talked about it, and that is you get these things called Lamel zeros. And so you don't have it's typically one thinks of just the focal spot. Well, it's a focal volume because there's a long range over which the energy is roughly the same, or this sort of a quasi-Rayleigh range, if you will. But now it turns out for a tight focus, you get these zeros. And then these zeros now mean they're right on axis. So that does some things that we're still studying to see how that works. So we know how to handle that, at least analytically. And so we're trying to see what that does. Now, that's not the only problem that one has. Is now their aberrations will cause even more issues that one has to deal with. And so bottom line is, yes, you lose energy. Roughly half the energy is lost by taking this flat top. But you get a lot more energy in, and so it's easier to handle. And you basically get the flat top for free because when you're going to saturate your gain, that's what happens. You saturate the gain in the middle, and then it just migrates to the outside, and that's how you get your flat top. So that part we know how to handle. It turns out that if you were looking at the trying to articulate what the field looks like, that's not so trivial. And you need to look at a vector component. It's a scalar response to the the field is incorrect. So you need to look at the vector components. So you can imagine that you have these vector components pointing in different directions, and coming off the mirrors, they point in strange directions. All of that has to be taken into account in order to get the right field. Another issue that happens at these really intense fields is because you've been told all your life that light is a transverse field, okay? And that you only have to worry about the electric field transverse to the propagation, which is correct for a plane wave. But imagine now you have a limited size beam, it's no longer a plane wave. And now what you end up with is longitudinal components. Those longitudinal components change the game. Because now you have electric fields that are pointing in the vertical direction, but you also have one in the longitudinal direction. You also have a magnetic field in the longitudinal direction. So when the electrons come off, they not only see the electric field and the magnetic fields that are perpendicular to the K vector, there are also longitudinal components. All those have to be taken into account. The higher the intensity, the larger those components are, and they too can be relativistic. And that just makes a headache, and you've got to keep track of all of that.
Thank you for the really thoughtful response. I think we have two more questions. The first is from Denmark, Lisma, where they ask, does four-wave mixin produce any particle or interference that affects the overall result in the vacuum? And what kind of nonlinearity do you see?
Okay, first of all, these experiments have never been done. These are design experiments. And we're not working on those experiments. The people who are working on these experiments are trying to work on this. Now, the four-wave mixing is really from the vacuum. And so in order to see this, there are no perturbations from other gases because those perturbations would be much larger than what you would see from the vacuum. So basically, again, you have to have a pure, so to speak, vacuum, which means that you have to have fewer than a tenth of a real particle in your focal volume during your experiment. So there aren't any perturbations in the usual sense of scattering noises that you mostly have in a four-wave mixing type of experiment because you're only looking at the vacuum. Now, it's not so trivial because there are other issues that you have to worry about. When you think of a weak laser and you think of high precision, you think of the laser, you know exactly where the laser beam is. Okay? You can measure where it is. It turns out for these big lasers, they fluctuate a lot. And now to get two lasers at the same point at the same time is hard. The four-wave mixing requires three lasers to be at the same point at the same time. And that just gets to be really difficult. So you will not have a signal on every shot. The complication is that even if they perfectly overlap, you're going to have probably less than one per shot. And now you take the fact that they're fluctuating, and that reduces it probably an order of magnitude or more. And so those are the real problems that you need to face. Now, there is a paper that came out recently where they've taken all these things into account and made a well, I don't know how aggressive the approximations were, but they estimate that if this opal laser were built, that they would be able to actually see a real signal. But we don't have lasers yet that are strong enough to actually see this. And so the experiment has not been done. So I can't tell you what the experimental issues are because nobody's done the experiment yet.
Dr. Hill, I had a question. You had mentioned vacuum birefringence. Is any team looking for vacuum Kerr effect or like a change in the refractive index in response to electric field?
Well, that would be similar. Okay, so there's a long history of looking at the birefringence, mostly with strong magnetic fields, which is the same thing. And so there are several experiments now looking for the birefringence, the Kerr effect. Don't know anybody looking for that. There are some strange theories about how the population of virtual particles and fluctuating ephemeral pairs can affect the speed of light. And so there's been some theories on that. But again, no experiments have been done. And so the only experiments I'm aware of are trying to look at the strongest effect. I have not seen Kerr effect. That doesn't mean nobody's thinking about it. I just haven't thought about it. Sorry.
Thank you.
Awesome. We have 4 more minutes and one more question. And it's from William Phillips, where they ask, concerning good vacuum ion pumps can get us to 10 to the negative 11 torr. Cryogenics could take us to 10 to the negative 14th, which is pretty hard to measure. What pressure can you get to, and how do you measure it?
Well, the experiments would start off with these pumps. Okay, so there's most of the experiments at the strong laser fields are only done in vacuums which are about 5 or 6 orders of magnitude worse than what you've talked about. They're usually around 10 to negative 4, maybe 5 millibar at best. In order to do the experiments we want to do, you'd have to start off in the 11 range, which is straightforward to do with a turbo pump. Working with a cryo pump and an ion pump are not going to be very effective because those need, in order to get the ranges that you talked about, you have to pump for a month or so. That is inconsistent with the type of experiments that we have to do. So the idea is to try to get down into maybe 10, which is fairly straightforward, and you can do that off the shelf. And then that produces an environment where you now can come in and you can instantaneously sweep out a vacuum. And how does that work? Well, I told you that the electrons come off of atoms. Basically, if you're at 10 to the 10, negative 10, you basically only have to worry about hydrogen. Maybe you have an argon floating around here and there, but it's mostly just hydrogen you have to worry about. So hydrogen ionizes very, very quickly. And so the only things that are left now are protons and electrons. And so these electrons, when they're born early in the pulse, so if you have a pulse that, let's say, is 10 to the 24 watts per square centimeter, now the electrons are born at about 10 to the 14. And so between 10 to the 14 and 10 to the 24, that's 10 orders of magnitude, those electrons are easily swept out of the beam with the laser. The protons at 10 to the 24 will also start to be swept out as well. So you can create a local instantaneous vacuum starting at around 10 to the negative 10 or so. 11 would be a little bit better. You don't need to do heroic efforts in order to for the pump, because in order to do that, you have to have pristine conditions. You have glass cells. You clearly have metal gaskets, and like I said, you're pumping for months. We don't have that luxury of doing these experiments. We have to be able to. We don't even. Most of these chambers that are used to do these experiments still have rubber O-rings. So the vacuums, the best vacuums that we have seen are in the high 7s. So we're nowhere close to being at state of the art in terms of vacuum pumps. So we have to rely on other means to create a vacuum, an instantaneous vacuum. So the issue now is you create the vacuum, the mean free path's larger than the chamber. So once you sweep these electrons out, they're going fast, of course, so they're going to bounce off the walls and come back. But that still takes a few nanoseconds. So you have, and the experiments are over within 20 femtoseconds. So in 20 femtoseconds, you can do an experiment by sweeping, making an instantaneous vacuum. That's the plan.
Thank you.
All right.
That's all for questions, and I'm going to hand it over to Alan to close us out.
Okay.
Thank you again, Dr. Hill, for that really interesting talk. And thank you to the audience for coming. We appreciate your support. And tune in for the next KITP NSBP Innovate talk. And we thank everyone who helped us get here. Thank you and have a good day.
All right. Thank you.